Okay, so welcome to GER Hub. In today's class, we shall be discussing our we shall be having our fourth discussion on set theory. Today, we'll be focused on set operations. Okay, so we'll be dealing with set operations in this class. This may be the second to the last class, or we may need one more class to conclude our discussions on set theory. So welcome from all over the world. I have put the link in the description to all the videos, starting from the first class we had on set to the last class we had on set. So you can check out the link in the description of this video. Thank you very much. Please smash a like on the video, subscribe to the channel if you haven't subscribed to the channel. Let's begin. So we are still discussing set theory. We are still discussing set theory, guys. And today is our fourth class. So this is our fourth class on set theory. This is our fourth class on set theory. Okay. So what shall we be doing today? Our focus will be set operations. Set operations. That will be our focus in this class. And what operations would we be looking at? Number one, we shall look at the first operation we shall be looking at will be intersection of sets. Okay, the intersection operation. So this is the operation we'll be looking at. The second operation we'll be looking at will be the union operation of sets. The third operation we shall be looking at will be the complement operation of sets. Okay, then the fourth, we shall consider what we call the difference operation of sets, and we will then consider the symmetric difference of sets. So we shall be considering all these operations. Please take note. These will be the focus in today's class. So quickly, without much waste of time, let us begin. So let's start with the first operation. The intersection of sets. How are we going to proceed with explanations on this? Please take note, guys. What we shall be doing will be to define each operation and then move over to examples. Okay? So let's take number one, intersection of sets. So I'm going to say, let A and B be two non-empty sets. Let A and B be two non-empty sets. Yeah, Modi Ayabon, welcome to class. Thank you very much. Biochemistry, thank you very much. You're welcome. I really appreciate that. So let A and B be two non-empty sets. The first operation, please, if you are just joining us, take note, our focus in today's class on set theory, being the fourth class on set theory, is on set operations. So we shall be considering set operations. I have listed out all the operations we shall be looking at in this order. Intersection of sets. Intersection is an operation on set theory. Union of set. Union is an operation in set theory. Complement of set. Complement is an operation in set theory. So also do we have difference, symmetric difference. There is even what we call the product of sets. That will be for another class. Now, let's start with the first one. So welcome all of you to the class. As you come into the class, please do well to smash a like on the video. Department, let me know where you are watching from. It's really, really important so that I can acknowledge you. Thank you very much for the support. Now, let A and B be two sets. We want to define the intersection of sets. So I'm taking two sets into consideration. So if A and B are two sets, then the intersection of the set A and the set B is a new set. The intersection is a new set formed by taking elements. Adam, Daniel, Jagabal, welcome to class. Thank you very much. Thank you for the support. That's a year 3 student. I'm correct. Yes. So we want to define the intersection of sets. So we are saying let two sets A and B be given to us as non-empty sets. Then the intersection of A, what we call the intersection of A and B, is a new set that is formed by taking elements that are common. Elements that are common to both A and B. So the intersection of two sets or more sets, as the case may be, is a new set that is formed when you take all the elements from each set that are common to all the sets. So if, for example, let's look at this, for example, that A is a set that contains 1, 2, 3, and B is a set that contains 3, 4, 5. Now, what we call the intersection of A and B, the intersection of A and B, Isaac Ayambe, welcome to class. Thank you very much. Biochemistry, welcome. So what we call the intersection of A and B, the intersection of A and B will be the set. It is a new set on its own that contains elements that are common to the two sets in question. Now, if you look at A, the set A, you will notice that the set A has 3 elements, 1, 2, and 3. If you look at the set B, you will notice that it contains 3 elements also, 3, 4, and 5. Now, what you will notice is that in set A, there is 3, and in set B, there is 3. So, the new set formed that is called the intersection of set A and B is the set that contains the elements that are common to both A and B, and that set is a set that contains 3 as the element common to A and B. Now, we don't write intersection of A and B in this manner. We use a symbol. We use this symbol, and this symbol, please, is called cap. Okay? So the symbol cap is used to represent intersection operation. Okay? So rather than write intersection of A and B equals 3, we write A cap B is equal to the set, the singleton. Remember, in yesterday's class, we said a singleton is a set that contains only one element. So please take note. What is the intersection of two sets? Intersection is a set operation. It combines two sets. What is the intersection of two sets? A set that is formed by taking elements that are common to the two sets. So, as I've given you this example, looking at this example, 3 is the element common to both A and B. And as such, when we form the new set called the intersection of A and B, it will contain only 3, because by definition, the intersection must contain elements common to both sets. Now, what symbol do you use to represent the intersection operation? It is this symbol I'm pointing at. And what is the symbol called? It is called cap. Okay? So we use the cap symbol to represent intersection. As such, instead of saying intersection of A and B equals 3, what we rather do or use is to say A cap B is equal to 3. Okay? Now, that is one example. Let us look at another example. Let's assume that I give you a set C that contains 4, 5, 9, 2, and 3. And I give you another set D that contains 1, 2, 5, 4, 9, and 7. Now, looking at this set, what would you call C cap D? C cap D will be the set, the intersection of the two sets. It will be a new set that contains elements that are found both in C and D. Now, what are the elements? What elements can you find in C that you can find in D? Let's take them. There is 4 in C and there is 4 in C. Okay, so 4 is common to both sets. There is 5 in C and there is 5 in D. So 5 is also common. There is 9 in C and there is 9 in D. So 9 is common. There is 2 in C and there is 2 in D. So it is also common. Whereas there is 3 in C, there is no 3 in D. And whereas there is 1 and 7 in D, there are no 1 and 7 in D. As such, the intersection of C and D will be the set that contains these elements that are common: 4, 5, 9, and 2. So this is how we form the intersection. The intersection is the set that contains elements that are found in both sets. Now, let us use a more technical example, and I really want you to pay attention, guys. Let's use a more technical example. Now, let me give you a set like this. So let's assume that we have a set like this. Give me a moment. Okay, so now let's look at an example like this. What if you are given an example like this? Now, if you remember, if you attended my previous class, you will remember I had told you that all students, all of you, must know how to read and interpret set theoretic notation or set builder notation. I emphasize that because your exams, because your tests, because the materials you read most times will not give you simple sets or simple expressions for set. They would rather give you expressions in what we call set builder notation or set theoretic notation. Now, this is how your exam questions may come up. And if you don't know how to interpret or read this thing, you won't know how to interpret it. So let's start with interpreting this set and this set. Now, please take note. How do you read this? I'm going to read it for you and I'm going to write it out. Please, if you don't know how to read, just hear me read it out and then read after me. Okay, in your room or wherever you are. The set A is the set of all elements X. Let me write it out. If you want to read this in set theory, it will be read as the set, because remember, capital letters represent sets. So the set A is the set of all elements small x. Okay, so I've read up to this point. The set A is the set of all elements small x. Now, this bar in set theory is read as such that. So whenever you see a bar or a colon, they are read in set theoretic notation as such that. So let's go over it again. The set A is the set of all elements small x such that, so I'm going to put here such that x, this symbol, please take note, this symbol here is called the membership symbol, and it is read as a member of, or an element of, or a component of. So I'm going to go back again and say the set A is the set of all elements small x such that x is an element or member of the natural number system. The natural number system. Now, why am I saying an element or member of the natural number system? It is because this symbol, this type of N that has double stroke, is called the natural number system. Okay? We use that number or that symbol to represent the natural number system. This particular symbol here. So let's read it again. The set A is the set of all elements small x such that x is a member of the natural number system. In some way, you could just go straight by saying it is the set of all elements small x such that x is a natural number. You won't be wrong. Okay? Now, how do we read comma in set theory? Wherever you find a comma in a set builder notation, it is read as and. Okay? So it will now be the set A is the set of all elements small x such that x is a member of the natural number system and x lies between 0 and 3. X lies between 0 and 3 and can be 0, it can be 3. Why? Because there is an equal to here permitting the possibility of x being 0 and x being 3. So I'm going to say the set A is the set of all elements small x such that x is an element or member of the natural number system, okay? And x lies between 0 and 3 included. You see it? So once you can read set theoretic notation, you can now make sense of what is written here. Now the question is, the x we are looking at must be a natural number. That one is sure. Now the question is, what natural number lies between 0 and 3? That can be 0 and that can be 3. So we will say 0. Please take note, there is a school of thought that argues that 0 is a natural number. I belong to that school of thought. There is another school of thought that argues that 0 is not a natural number. So that's a discussion for another day. Now, 0 to me is a natural number. So I'm going to say 0, 1, 2, and 3. Now, looking at it, I have just used set theoretic notation. My ability to read and interpret set theoretic notation is what has made me know that the set we are referring to contains 4 elements, 0, 1, 2, and 3. Now, once you finish reading that one, let's read the other one. This one will read as the set B is the set of all elements small x such that x is a natural number and x is 2. So this set contains just 2. Welcome, Endurance Opeta. Welcome. Thank you, Endurance. This is also another support student from the year 3 class. Thank you very much. So now you can now see that we have 2 sets, this set and this set. Now, if you want to find the intersection of A and B, now that we've been able to interpret set builder notation and to know the exact set, you will now notice that the set A intersection B is the set that contains elements that are common to A and B. And what elements would you find common to A and B? It is the element 2. So A intersection B is 2. So please take note of that. That intersection means it is a set. We are referring to a set, a new set that contains elements common to both sets. Okay? Elements common to both sets. Now, I'm going to extend this theory a little bit. What if, the question is, what symbol, if I have, is it possible to have a set 1, A1, a set A2, a second set, a set A3, up to a set AN? Let's assume that n is a number we don't know yet. So what if I want to say, I want to find the intersection, the elements common to A1, A2, A3, up to AN? We symbolically write it in this manner. So if you want to find the intersection of n sets, n different sets, A1, A2, A3 to AN, you write it like this. In shorthand notation, this same thing that I've written in this manner, that's A1 cap, A2 cap, A3 cap, up to cap AN. If you want to write this mathematical expression of the intersection of n sets, all you have to do is to put the cap notation, put an iteration from I equals 1 to n. I starts from 1 and ends at n. So you just do this and then put here AI. So the intersection of n sets, starting from the first set to the nth set, can be expressed in shorthand notation as this. So whenever you see this, it means A1 intersection, A2 intersection, A3 intersection, ellipses, because the counting continues to AN. So this represents the intersection of n sets, if you don't know what n is. Okay? So we are going to look at this when we get into problem solving. I'm going to be solving so many problems. At that point in time, I want all the 100 level students, please, from any faculty you are, join the solution. As soon as we are done with set theory, the classes on set theory, I'm going to solve past questions on set theory. So please be ready for that problem solving session. Now we are just explaining the concept of set theory, but a time will come after the class on set theory where we shall be discussing in detail from different past questions on set theory that you can meet again in your exam. So please take note of that. That being said, let us move to the next operation. Let's move to the next operation. So immediately after the intersection of sets comes another operation, which we will call the union of sets. The union of sets. So the union is another set operation. So how do we define the union of sets? So I'm going to say, let A, I'm using two sets. Let A and B be two non-empty sets. Let A and B be two non-empty sets. Okay? Now, if A and B are two non-empty sets, then the union of set A and set B is a new set that contains elements that are found in either A or B or both of them. Okay, so unlike the intersection, the union is a set that is found, a new set that is formed by taking elements that are found in A alone, added to elements that are found in B alone, added to elements that are found in both of them. That is what we mean by either A or B or both. Okay, now there is something I have to that all the time do we define grammar or English sentences. If you were to describe the definition of the intersection of two sets, if you were to define the intersection of two sets, please take note. All you would do will be to say A intersection B, that is writing it in set builder notation, is the set of all elements X such that X is a member of A, X is a member, and X is a member of B. Okay? So if X is a member of A and X is a member of B, then A intersection B is the intersection. Okay? So the intersection of A and B is the set of all elements that are found in A as well as in B. Now, if you come over to the union, if you want to do same to the union, please take note. For you to represent the union operation, we use this symbol. This symbol is called cup, whereas the other one was called cap. This one is called cup. So if I want to say A union B or write A union B in set theory, we will write A cup B. A cup B is read as A union B. Remember, the union of two sets is the set that contains elements found either in A or B or both of them. So this symbol is used to represent union and it is called cup. Now, A cup B will mean A union B. So A union B now is defined as the set of all elements X such that X is a member of A, or X is a member of B, or X is a member of, and X is a member of A intersection B. Okay, so this is me writing mathematically what I have just said using this statement. Okay, so if you don't want to use this statement, this story statement in English language, you could use this statement mathematically to define. This statement is the definition you have just said. Okay, so they mean the same thing. Now let's take an example. But before we take an example, let's do the same thing. What if I want to find the union of n sets, say A1, A2, A3, up to, we write it in shorthand notation. We put the cup symbol and put an iteration I equals 1 to n, meaning that you are combining n sets under union, A1, set A2, set A3, up to set AN under union. So I'm going to put here AI. So AI, starting from I equals 1 to n in union, gives the shorthand notation of all these. Now, what if you now say you have an example and you have a set A that contains 4, 5, 6, and another set B that contains 1, 2, 3, and 6. If you have these two sets and you are asked to find A union B, what will A union B be? A union B will be the set that contains elements that are found only in A. Okay? First of all, let's take the elements that are found only in A. The elements that are found only in A and not in B are 4 and 5. Come over to B. What elements do you find only in B? You have 1, 2, and 3. Then comes, what elements do you find in both of them? You have 6. This will give you the union. Okay? So the union of the two sets is formed when you take elements that are found only in the first set, the second set, and both of them. Okay? So it is the set that contains elements found in either A, as in this case, or B, or both of them. Now, what have I done? I started with forming my union by taking the elements you find only in A. You will notice I did not pick 6, and that is because 6 is found in B. So I picked the elements that are found only in A first, and I wrote them into my union, 4 and 5. I went into B and picked the elements that are found only in B but not in A. I took 1, 2, and 3, and I wrote them out in my union. Then came the last step, which was taking what was common to both of them, 6 and 6, and I wrote it down. So that gives my union. Let us take another example. What if you have C equals orange, mango, pineapple, and D contains orange, mango? What will be the union of these two sets? The union of these two sets will be C union D, a new set that is formed by taking elements that are found either in C or in D or both of them. So let's start. In C union D, you will take the elements that are found only in C. The elements that are found only in C, in this case is just one, is pineapple. Then comes the elements that are found only in D. There are no elements that are found only in D. Rather, you have elements that are found common to both C and D, and they are mango and pineapple. So you will notice that I did not repeat any element. So the elements you find in C union D are the elements orange, mango, and pineapple, because you already have orange and mango in D. So let's now take a set theoretic problem. Let's bring back that problem we had, but in a more refined form, the one I gave earlier on. So let's assume that you were given this in your exam or in your test to find. You were told X is the set of all elements X such that X is a natural number and X lies between 0 and 3. Let's modify the problem a little bit. Now, I'm giving you another set B such that B is the set of all elements X such that X is a natural number and lies between 0 and 3. You will notice that there is a difference here. In my first set, there is the equal to there is the equal to sign. I'm using the less than or equal to sign. In this one, I'm using the strict less than sign. Now, this set here, the only natural numbers that lie between 0 and 3, with 0 and 3 included, are 0, 1, 2, and 3. Then, if you come over to the next case, the only natural numbers that are found between 0 and 3 without 0 and 3 are just 1 and 2. So the question now is, what is the union of A and B? The union of A and B will be the set that contains all the elements found in A alone, B alone, or both of them. And that will be 0, 1, 0 and 3 are found in A alone, and 1 and 2 are found in both of them. So this will give you the union. So all you have to do to form the union of two sets is to combine all the elements in the two sets, avoiding repetition. So don't make the mistake of doing this. A union B is 0, 1, 2, 3, 1, 2. You will be wrong. Remember, in set, we said that elements of a set are unique, and they are unique and distinct. So in set, this set here is the same as 0, 1, 2, 3, because 1 and 1 counts only one time, and 2 and 2 would only count one time. There is no repetition. Okay, so I'm going to not say anything more on the union of the sets or the union of sets as an operation. Let us now go to the third operation we are going to be looking at. The third operation we are going to be looking at will be the complement of a set. The complement of a set. That will be the third operation, complement of a set. Now, notice one thing about the two previous operations we've looked at. Intersection was an operation that combines two sets or more. Union of a set was another operation in set theory that combines two sets or more. However, complement of a set does not combine any set. It only deals with one set. So this is what we are going to say. If you are going to take the complement of a set, it must be in relation to another set. Okay, in the first example, so if I gave my answer as 1, 2, 3, 4, 5, 6, would I be, please, could you send in that question again? Could you send in that question again, Daniel? Thank you. Send in that question again. It's off my screen. I want to see that question you just asked again. Okay, give me a moment. Let me see if I can bring that out. I want to see that chat. Okay. Okay, I've seen the question now. You said in the first example, if I gave my answer as 1, 2, 3, 4, 5, 6, if I gave my answer as 1, 2, 3, 4, 5, 6, would I be marked right? Would I be marked right? What example? Okay. 1, 2, 3, 4, 5, 6. Yes, you will be marked right, because we have said that you are still correct, because we say that the order of elements, the order of arrangement of elements in a set does not really matter. Okay, so whether you put it as 1, 2, 3, 4, 5, 6, or you put it as 1, 3, 5, 2, 6, and 4, you are still correct, provided all the elements are complete. You are still correct. Order does not matter. Thank you very much for that question. So let's go on. So if you are looking at the complement of a set, it must be in relation to the universal set or a larger set. Okay, so let A be a subset of the universal set. Let A be a subset of the universal set mu. Okay, if you are talking about complement of a set, it must be in relation to a larger set, particularly in this case, maybe the universal set. So if there is a set A that is a subset of the universal set, that is A is a subset of the universal set, or particularly let's use the proper subset, this. Then what we call the complement, then the complement of A. What would we call the complement of A? Then the complement of A denoted by A prime or AC is a set that contains elements that are found in the universal set but not in A. So what we call the complement of A, you cannot start talking about the complement of a set if you are not comparing it with a larger set. That is what I want all of you to know. If you must find the complement of a set, somebody cannot just walk up to you and say, please, what is the complement of U? The complement of U must be taken in relation to another person, probably someone bigger than you. The complement of a set must be taken in relation to a larger set, probably the universal set. So what am I saying? I'm saying that if A is a set and there is a universal set, which is, of course, a superset to A, that is, A is a subset of the universal set, I am saying that the complement of A must be taken in relation to the universal set. So what then is the complement of A? It is a set that contains every element you find in the universal set that are not found in A. Let's see what that means. So let's assume that A is a set that contains 4, 5, and 7. And B, which is my universal set in this case, is a set that contains 1, 2, 3. It's a set that contains 1, 2, 3, 4, 5, 6, and 7. Now, if you want to find A complement will be all those elements, will be a set that contains all the elements you find in the universal set that are not found in A. What are the elements found in A? 4, 5, 6, and 4, 5, 7. What elements do you find in the universal set that you do not find in A? Will form a set called the complement. So let's write all the elements you find in the universal set that are not found in A. In A, I don't find 1, so I'm going to put 1 here. In A, I don't find 2, so I'm going to put 2 in the complement. In A, I don't find 3, so I'm going to put 3 in the complement. In A, I don't have 6, so I'm going to put 6 in the complement. So the complement of A is in relation to mu, the set 1, 2, 3, 6. Okay? So complement simply means a set that is formed containing elements in a larger set of reference not found in the main set. So this will be the complement of A. All you have to do is to extract the elements in the universal set that are not in A, and that will give you the complement of A. Now, please take note of these two things before I forget. Remember, we are done in intersection of sets. Let me show you something that you can infer from the intersection of sets. So if you have A intersection B, the question is, if A has nothing, if A intersection B is such that A has no element that B has, there is nothing common to A and B, then you would have an empty set. So this empty set will be called disjoint, would imply that A and B are disjoint. So it gives rise to, the intersection of two sets gives rise to what we call disjoint sets. So what are disjoint sets? Disjoint sets, or two sets are said to be disjoint. Disjoint sets are sets that have no element in common. So if two or more sets have no elements in common, their intersection will give you the empty set. So if I now ask you, if I tell you that there are two sets, B and C, and their intersection gives me the empty set, their intersection does not give me the empty set, what would you say about B and C? They are not disjoint. They are not disjoint. They are not disjoint. But if I have two sets, D and E, and their intersection gives us the empty set, we are going to say that they are disjoint. So the idea of disjoint set is coming from an implication of the idea of intersection. Okay, so from the idea of intersection, you can have disjoint sets. Now, there is something else I want you to know. What idea can we get from complement of a set? From the idea of complement of a set, we can now have what we call the concept of we can have this implication rather. So if AC is the complement, if AC is the complement of a set A, then A union AC will give us the universal set. Okay? So if you combine a set with its complement, it will give you the universal set. And if you combine a set A in intersection with its complement, it will give you the empty set. It means that the combination in intersection of a set and its complement is disjoint, whereas the combination of a set and its complement in union can give you the universal set if those are the two sets under consideration. So that being said, let us now go over to the difference of two sets. But let me give you an example of what I have just said. So look at it this way. A is a set that contains 1, 2, and 3. And B is a set that contains 3, 4, 2, and 5. Now, what is A intersection B? Or rather, let's do it this way. Let's do it this way. So I have, let me add 1 here. Let me add 1 to the list. So what is the complement of A? The complement of A will be the set that contains 4 and 5. Okay? Now I'm taking B as my universal set and I'm taking A as the subset. Notice that if A is the subset of B, then A complement will be all the elements you have, will be the set that contains all the elements you have in B, the universal set that are not found in A. Now, look at it critically. A contains 1, 2, and 3, and B contains 4 and 5. What is A intersection A complement? You will notice that because A complement is the complement of A, they have nothing in common. So I'm saying that the complement of a set in intersection with itself will give you Gloria Ago. Good evening. Welcome from biochemistry. I have a lot of biochemistry students joining today's live class. God bless you all. I really, really appreciate. Please tell your guys or your colleagues about the class, that classes are going on online. Thank you very much. Thank you very much. Please feel free to ask questions. And if you haven't subscribed to the channel, please support this channel by clicking the subscription button and endeavor to tell your friends about the class. Also do well to share the videos to your platforms, share the videos to your colleagues, okay? So that they can be a part of this experience. Something is actually going on here. Very soon, we will be going into solving questions in set theory once we are done with set theory before moving to the next topic. Thank you very much. Please smash a like on the video and tell your colleagues about this class. Thank you very much. I really appreciate all of you. God bless you. Now, so A intersection A complement is empty. You can see it because there is nothing common to A complement and A. Now, what is the union of A and A complement? You will notice that the union will give you 1, 2, 3, 4, and 5. So this union gives B, which is the universal set, whereas the complement and the set A itself in intersection gives the empty set. So that is what I want you to know. Quickly, let us now go to definition or operation number 4. Operation number 4 is difference of two sets. Paul Elizabeth from computer science, thank you very much for joining the class. Welcome to the class. Thank you very much. Please, if you are just joining the class, don't mind the fact that we've gone far in the class. You can, after this class, watch the video all over again, or you can drag the slide down to the beginning to watch where we began from and all we have said so far, okay? But feel free, even after the class, to drop a question. If you have any question, feel free to ask. Don't be shy, don't be scared. I am one of you. Please feel free to ask any question at all. You can drop a comment in the comment section and I will attend to them once I see them. Thank you very much. So let's look at difference of sets. Okay, so difference is an operation in set. So if there are two sets, let A and B be two sets. Okay, let A and B be two sets. The difference, the difference between A and B, written as A minus B or A backward slash B, is a set that contains elements found only in A. Okay, so if there are two sets, A and B, A contains 1, 2, 3, and B contains 3, 6, 5. The question is, what is A minus B, which is also written as A minus B? That is, this slash, backward slash, is read as difference B. Okay? So A minus B, if you don't want to write it in this form, you can write it as A backward slash B, read as A minus B also. A minus B will be the set that contains elements found only in A. Okay? Elements found only in A, but not in B. And what are the elements found only in A? If you compare the set A with the set B, you will notice that the elements that are found only in A, you don't find in B, are 1 and 2. So A minus B is 1 and 2. Now, the same way you can compute A minus B, you can also compute B minus A. B minus A is B backward slash A, and it is the set that contains elements found only in B, but not in A. So looking at the two sets, what elements do you find only in B that you don't find in A? You will notice that the elements you find only in B, not in A, are 6 and 5. So I'm going to write here 6 and 5. So it is that simple. Let's take another example on that. Let's take another example, and I'm going to tell you something you need to know about that set. Now, let's take another example on that. So if I have a set now that contains E, I, O, U, and I have another set that contains A, E, I, O, U. Now, the question is, class, what is A minus B, also written as A backward slash B? A minus B, remember, is the set that contains, in comparison with B, it is the set that contains elements found only in A. So what elements do you find only in A, but not in B? You will notice that there are no elements found only in A that you don't find in B. So it means that A minus B is empty, which is written as the empty set. Now, whereas A minus B is empty, what about B minus A? Also written as B backward slash A. B minus A contains the element found only in B, but not in A. And what element is that? Okora Joseph, welcome to the class. Thank you very much. What department are you? In what department are you? Please let us know. Welcome to class. So B minus A is the set that contains elements found only in A. B minus A contains elements found only in B, but not in A. So I'm going to write A here. It is the set that contains A as its only element. Now, please take note of something. That if you don't want to write, okay, Okora Joseph, welcome, information system, welcome. Thank you very much. I really appreciate. So A minus B can be written as A intersection B complement. This is another way of writing A minus B. If you don't want to write it as this or this or this, so anyone you choose to write represents A minus B. Similarly, B minus A, which is the set that contains only elements found in B in relation to A, will be A intersection B, but in this case, A will carry the complement. So this is the same as B minus A. Now, that being said, let us now move over to the last operation I want us to look at tonight. It is called, operation number 5 is called Tom Joseph, welcome. Thank you very much. Is that an answer you were giving me? I think you were giving me an answer to the last problem. You are correct. If that's an answer to the last problem, you are very, very correct. So B minus A. Let's now look at what we call symmetric difference. Symmetric difference. Okay, so we use this symbol delta to represent symmetric difference. So the symbol delta represents symmetric difference, guys. Now, what is the symmetric difference between two sets A and B? So if I give you a set A, let A and B be two sets. Then the symmetric difference between sets A and B is the union of A minus B and B minus A. So it means that the symmetric difference of A and B written as A A delta B, okay, the symmetric difference between A and B written as A delta B is equal to the set that contains the union of A minus B and B minus A. So if you unite A minus B and B minus A, it will give you what we call the symmetric difference of A and B. Let's take these examples we had above. Let's consider the examples we had above. Now look at what was my, let's come over to this example. What if I ask you for the symmetric difference between A and B using this example now? It will be, by definition, A minus B union B minus A. What was our A minus B? Our A minus B gave us the empty set. So it means I will be uniting the empty set, and B minus A gave us the set A. The union of the empty set and the set A is the set A itself. Okay? So that is how to operate the symmetric difference. Let's take a concrete example before we round up today's class. So let's look at a set A that contains 5, 9, 3, 6, 7. Let's look at a set B that contains 1, 2, 4, 5, 9, 8, and 6. Okay? So let's look at these two sets. For you to find A delta B, that is A symmetric difference B, then what you would have to do is to remember the definition says that A symmetric difference B is A difference B union B difference A. Now the question is, what is A difference B? Just give me a moment. Give me a moment, guys. Just give me a moment. Point that stuff here, please. Okay. Just give me a moment. I will be with you. Yeah. Okay. Oh, this shows that we are truly in Nigeria. Okay. So let's round up this class with this example. I'm going to round it up. So A minus B will give you the elements you find only in A, and the elements you find only in A, just focus on the problem. Don't mind NEPA. We are in Nigeria. So A minus B will give you 5, 9. Okay. And what elements do you find only in A? You will notice we have 7 as an element found only in A. 3 is also an element found only in A. Okay, so that is A minus B. The elements you find only in A are 7 and 3. Now let's go over to the elements you find only in B. The elements you find only in B are 1 and 2, okay, and 4. Good. There is 8 also. These are the elements found only in B. So for you to get A, Tom Joseph, don't mind them. So let's conclude with saying A difference B will give you, I was actually using a generator. I wasn't even using NEPA light. I was actually using a generator, not NEPA light. So I don't know why it went off, because there's enough fuel in that generator. So I'm going to check it. It could be oil. So let's see. And that won't stop us from learning. So A, the symmetric difference B would give you the union of A forward backward slash B, that is A minus B, and B minus A. So that will give us 7, 3 union 1, 2, 4, and 8. Now the union of these two sets will be what? 1, 2, 4, 873 or any order you want to arrange it. Okay, so that will give us the union. We are going to conclude this class tomorrow. We are going to stop here and we are going to conclude tomorrow with set operations and then move into Venn diagram and product of sets. After that, we are going to take problem solving on set theory. Thank you very much for being a part of this class. I really appreciate you guys. Sincerely appreciate all of you. Please smash a like on the video. Thank you for all your likes. Thank you for your shares of this video. Please, after this class, share the video to your platforms, share it to your colleagues. Tell them a class is going on online. They should be a part of the class. Thank you very much and good night.